Which was well studied Princeton, who will tell us about good and bad analogies in physics and machine learning.
All right, thanks a lot for the invitation and for coming to hear about this unusual topic. So I'll start with more or less pedagogical review of machine learning and deep learning. It's going to be pretty brief, but we'll touch on the main points, and then we'll transition to talking about how a physicist might try to tackle some of the problems that I'll present in deep learning. So the basic goal of machine learning is to take some observed data and then process it somehow and be able to make accurate predictions on unseen data. And this problem usually involves, or the way we usually do it, it involves three parts. So first we start with the data that we collected somehow by, let's say, doing an experiment. And typically this has the form of pairs of inputs and labels. So let's say we have n of these samples. And so you can imagine as a simple case, let's say we just measured, we have our inputs x and we measured some outputs y and they look something like this. And so the goal is then to, and let's say in this case we're imagining that these y's are coming from some underlying unknown function big F. And so what we're going to have to do is we're going to take this points and, for example, fit some function through it. And then given a new point x, we're going to make a prediction on y. So that's the first thing we start with. The next step is we choose a class of models, f theta of x. And this class is parameterized by some tunable parameters theta. And hopefully, if we did it right, this class of models will include some models which will be able to explain the data well and be able to also make good predictions on unseen samples. And this is generally true for machine learning. Now, what we do in deep learning, which will be what I will focus on, is we choose a particular, or we choose our class of models out of a particular set, which has the property that it's basically a composition of some basic computational units. So I'm going to write down the simplest deep learning model that one can have. It's going to be a neural network with one hidden layer. So I'll just write down what this function is. So what we're doing here, we're taking our input, which is a d-dimensional vector. We're acting on it with some linear transformation parameterized by this matrix W prime. Then we're acting with a nonlinear function sigma. We have to choose what this function is. Here's a very typical choice these days. The most common choice is called the rectified linear unit. It's a very simple function. It just looks like this. So that's it. Very simple. Then we act with another linear transformation, again parameterized by some more parameters W, and that's our output. And these parameters theta, I call theta collectively all the tunable parameters in our model. All right, so we defined a class of models. This thing also has a pictorial representation, which I'm sure some of you have seen. So we sort of think of this as being organized in layers. We have the first layer is the input layer, so we have d inputs because x is a d-dimensional vector. Then each neuron here, each of these circles I will call a neuron. Each neuron here is connected to all the others through this weight matrix W prime. And so each neuron here will collect its inputs weighted by W prime. I will act at each neuron with this nonlinearity, then act with another linear transformation parameterized by W, and this will be the output of the model. All right?
What is sigma in this picture?
You can imagine that each neuron acts with a linear transformation, and before the output leaves, it sort of acts with sigma. So each component separately acts with sigma. Right? All right, so this is a class of models we can consider. This used to be called deep learning. These days, this is called shallow learning because it only has one hidden layer. But yeah, okay. So things have definitely changed. The next step is, so we have this whole class of models. We're going to have to choose one. So we're going to have to choose a model that has the properties we want. And typically, the way we do this is we transform this into an optimization problem. So we're going to do optimization. What this means is that we're going to define a loss function or error function, a function of the parameters. And we're going to try, it sort of captures the error. So for a particular model, it's going to capture how bad are our predictions compared to the actual observed labels. And we're going to try to minimize this function and hopefully get a good model out of it. So in this particular example that we've been following, here's a typical choice for the loss function. We're taking the mean over all the observed samples. And we're summing, or we're taking the mean over the squared errors. So for each sample, we're computing our model's prediction. We're comparing it with the label that we observed. We're just summing these squared errors. And so this captures our error. We're going to have to try and minimize this function. And the way we minimize this function in deep learning is to use gradient descent. So in this example and in all the other examples that people use in deep learning, the models are differentiable almost everywhere. And so we can always take the gradient and try to minimize in this way. And so doing gradient descent means that we start out with some initial value for all of our parameters. So again, this theta was this vector of parameters. So it's going to be initial values for these weights. And then we evolve by, at each step, we compute the gradient. And then we take a small step in the other direction. And this parameter, this is called the learning rate. And there's some trade-off here. You don't want to take this too big because then your linear approximation breaks down. You don't want to take this too small because then you're not going anywhere. And so you have to somehow choose this parameter. You keep iterating this procedure until you're happy with the performance. All right? So this is the basic deep learning setup. Now, this only takes us so far in terms of real-world performance. And I'm just going to mention a few generalizations of this basic setup, and then move on and focus on what are the actual questions that people ask on this. So any questions so far? Yeah.
Can you give an example, like of some real-world application of this kind of thing?
So this, like imagine you made some measurements of some, you change the voltage, you measure the current. So this is an example, and you want to now give it a new voltage, predict the current.
Why is it better than just fitting in mathematical with polynomials?
Yes. So I will come to you. You will see why. I will come to that. So fitting with polynomials, but maybe let me answer this now. So fitting with polynomials means that you have your inputs, and then you're making some decision about how you're going to process these inputs. In particular, you compute the monomials, and you feed that into the thing, right? And in many real-world applications, like I'm going to discuss image classification now, image classification, I will explain. People have spent whole careers trying to find what the right features are, what are the analogs of these monomials that will give good performance. The point of using these deep networks is that you can think of them as sort of figuring out what the right features are for you, and then the last step is like an ordinary classifier or an ordinary linear regression step that you would do anyway, but everything that happens before is sort of finding out what the right features are from the data.
I can understand, because you already made the decision. What is sigma? What is...
Yes, but you still have many tunable parameters. So you still have many different. It still has a lot of freedom of massaging this input data.
What is the meaning of this sigma? This particular one. Why is this one chosen often, or so any sigma will do?
Right. So all right. So to explain why this one is sort of good, let's think about the one that people sort of had before this. So the one that people had before this was called the sigmoid. this was like the popular choice before people figured this one out. And so this function just looks like this. Well, I can't draw, but you understand what I mean. And this function was motivated by biology, sort of, because you can think of each neuron as like not firing or firing, and then something happens in the middle. And this function turns out to be not a very good choice for a technical reason. And the technical reason is that as people, so one of the generalizations that you do here is just add more and more of these layers to make your capacity of the model bigger. And then you run into trouble because again, we have to compute the gradient in order to train. And what you find is that as you try to compute the gradient with respect to the layers or the respect to the weights in the deeper networks, most of the neurons in these forward layers end up saturating here or here. And so the gradient vanishes as you go into the network, and it just doesn't train. This does much better. It seems that just for the simple reason that it only saturates in one direction. I think it's not yet clear why. I don't think we understand the full story, but it definitely solves this vanishing gradient problem.
So how do you calculate the gradient? How do we do lots of experiments and see what it's like, or?
No, the gradient is computed. Yeah, the gradient can be, well, you see, the gradient is computed analytically, just starting with this function. And the reason this works is that there is a clever algorithm of doing this called backpropagation, which allows you to compute the gradient. So let's say here in this model we had p, or order p or p times d tunable parameters. Well, let's say p. So this gradient can be computed in order p time. And the whole trick behind backpropagation is the chain rule. So basically what you do is once you've computed the gradient back to some layer, you can reuse those results to compute the next ones.
You differentiate with respect to x or with respect to w?
Sorry, with respect to w. Always the parameters. I don't, yeah.
So in addition to the weight, people usually put bias on.
You can put, yeah, you can put bias. Yeah, you can add, so, right, you can add some parameters like this. Yeah, there are many. Yeah, I'm trying to stick to the simplistic.
The difference between these two choices. One is growing at infinity, and another is.
Exactly. That's why it seems that this is why this is solving the, yeah.
Mm-hmm. But one is sigma and one is sigma prime, right?
I'm sorry. Let me call it sigma tilde. Sorry. It's supposed to be a different function. Yes, it's definitely a big difference. Although either with, I mean, there aren't many theoretical results about these deep networks. Well, one thing you can show is that either with this choice or with this choice, if you have enough neurons in this hidden layer, you can approximate any function to arbitrary precision. So in that sense, it doesn't seem to matter, but for practical reasons, it does.
Like a universal computer in some sense?
Yeah. Well, it's a universal approximator.
Okay.
Yeah. Right. Good. So this is the basic setup, and now I will say a few words about. I mean, you see that with this, we're not going to be able to go very far. I'll say a few words about generalizations of this that people actually use in practice. So one generalization is the kind of problem that you can tackle with this. So far we talked about regression. This is where you have. This is sort of the natural thing you can maybe you sort of see in practice as a physicist if you work with experimental data. This is, again, where we have some underlying unknown function f, and we're trying to fit it. The other case, which in machine learning is much more prevalent, is classification. Here, what we're trying to model is a dependent probability distribution y given x. So the example to keep in mind for this is image classification. The inputs will be the pixel values of our image, and the labels will be something like, for example, what's in the image. So let's say we're trying to decide, does this image contain a dog, a cat, or a boat? So these will be the labels. Boat? Yes? No, I meant, sorry, boat. boat, or a goat, or whatever.
Classifier is better than ours.
Yeah. Right. So you choose a few classes like this, and you try to, and for each image you are told, so for each observed image in the data you are told what it contains by the label, and then you will try to learn and be shown new images, and you try to predict what's in these new images.
The computer predicts the probabilities, not the actual y.
Yes, you will get a probability distribution, and you will typically take the prediction will be the likeliest, the max likelihood one. Yeah, it's very useful. It's very useful to phrase this as a probability distribution question, even though we know for sure what the labels are on the inputs.
This function p should come with an error. Like the computer doesn't say 78%, but maybe 78 plus minus 10, because how does it know 78?
It's like its best guess. Its best guess is 78%.
It doesn't produce p, it produces an answer y.
No, it produces. Let me explain how you get the p, and then you'll see. It produces. What? Y are the labels. So y belongs, let's say, to like dog, cat. Fine. Let's say finite. It's 10. 10 of these. Just to keep it concrete.
General question: if the new data arrives,
Yeah.
and it's very noisy,
Yeah.
it's unlikely to be ever predicted. So probably there is some limitation or some assumption about existence of distribution, or there is some assumption of the new data which arrives. Correct?
Yeah, there exactly.
How to formulate it?
Let me answer this in a few minutes. Well, I won't have an answer, but let me address this in a larger context. I think the simple answer is we don't know, but.
We do the lottery every time.
Yeah, I mean, of course, if the new samples don't have any obvious relation to the old ones, then we'll not be able to do anything. There is an assumption that there is some underlying relation, which I don't know how to formalize.
Yeah. So my problem is then when I listen about, when I hear about,
Yes.
I always wait when this assumption will come, and they miss it. It never comes.
No,
Maybe you can formulate it in the beginning.
No, there is.
A set of data which we expected to predict. Obviously,
But
I don't have an answer. I don't have an answer for this.
I think is, at least I read on the internet, maybe it's not true, that this is already better than humans.
Yes.
So
Like the proof is in the pudding for now. For now, it works. And not this simple model, but a very similar model works on image classification with real-world noisy data. And it,
we may reverse the question. Assume that this model
better than
works.
humans.
Which data will
Better than humans.
fit this model?
yes, I don't have an answer. Well, maybe I'll give a partial. I'll give a partial answer to this. Okay, I'll give a partial answer.
You can mention stuff like actual results, maybe.
Yeah, I'm trying to. Yes.
I mean, like by how much is it better than humans?
I will. Yeah, I'm trying to. So this is this problem of classification. I do have to explain. I think right now this is disconnected from what I explained. So I just need to explain how we do classification with these networks. So the point is that we add some more neurons, one neuron for each class in our classification. And we do the same thing as we did before, but now we treat the outputs as unnormalized probabilities. And now we normalize them somehow, for example, by thinking of them as energies and fitting them into a Boltzmann distribution, and we're going to get like probabilities like that. So that,
Output is not a function, but a vector.
yes, output is a vector. Also in regression, you can make it a vector. Yes.
If you have Boltzmann probability, what's the Hamiltonian? Whatever fits.
Whatever fits. Yeah. And the Hamiltonian changes with each input, right? With each windows. Yeah. Yeah. So now. Yeah, okay, let me give, yeah, if it's too vague, let me give some actual results on image classification. So in typical models, what we have are, so let's say we can have a data set with like tens of thousands or hundreds of thousands of images that come in, and each one is labeled as belonging to one of 10 or 100 classes, or that is X. Well, and the label. Each one comes with a label. So it's pairs of X and Y.
More labels than X's? Or?
No. They come in pairs. Same number. Each image, you're just told what it is, right? And then state-of-the-art models that are trained on this.
N is the number of pixels.
No, N is the number of pictures. Pictures. Let's say each picture is 32 by 32 pixels, for example. Something like that. Right? So this is like D. This is what I call D. This is the training set. Okay? We train this on models, which are sort of this kind. And the number of parameters in the models can be hundreds of thousands, let's say up to tens of millions. This is very typical. W's. Right? And on these models, if you do it right and use the right architectures and so on, and these are real-world images, like you just took them with cameras, then you can get better than human performance on classification. You may ask, how can it be better than human performance if the labels were put there by humans, right? And the answer is that if you just go a bit into the details, you will see that, so first of all, a human will have a bit of a hard time with some of these data sets because some of the data sets that people use include things like, so let's say the ones with 100 classes, they can include like 20 different kinds of dogs or something, which an ordinary person wouldn't just not be able to classify. And that is what is meant by like better than human performance. It's better than a random person that you would take to look at the images. But it's just, I mean, for all practical purposes, it's just as good as you would do looking at these pictures.
I don't understand. You
Yeah.
take this data set and you do this gradient flow.
Yes.
And you get to the best possible fit.
Yes.
And then you compare that to a human?
No, not that. Then you have more samples. Let's say 10,000 more. Yeah. I'm sorry. Well, that depends with, let's say, 10,000 more. 10,000 more.
Which are not necessarily like looking the same as those.
They're different pictures.
Different pictures.
You start out by splitting these randomly. Yes.
And Wigman's question is actually to the point because you will probably start adding.
You're adding more
new
pictures
data.
now.
Yes, the whole question, of course, is not explaining the data we know, but explaining the data we have not seen yet. Otherwise, it's not interesting.
So you take this set to the 4 randomly out of the 10 to the 5.
Yes.
And then you compare the performance of the fitter to a human on those.
Yes. Yes, exactly. Unseen data. The whole question is about unseen data. Otherwise, it's like just pointless.
But I mean, obviously, if this 10 to the 4 is like garbage by accident, then it wouldn't work.
Exactly. Then it will not generalize well. That's right. That's right. That's the thing I wanna.
So that means that once you build this model, so you continue to grow this graph.
Yes.
By arriving to new data.
No. I don't continue to grow the graph. When I get new, if I do this by getting new data, I just do more gradient descent steps on the same graph. The graph is fixed, and the way I would treat more data is by doing more gradient, fine-tuning the parameters more and more. That's the dynamical aspect of it.
But that also means that this graph is kind of, it's random, but not very, very much random, right? So there's no big fluctuations within the graph. Right? That means that the data obey some rules.
Yeah, well.
They're random, but they're not too noisy, right?
Well.
Otherwise it will be also graph, but from which you can probably read more valuable information.
Well, I don't think, in this case, I don't think I have to prove anything because we have a proof of concept, like the humans can do this. And we're not like magical, right? So obviously there is some computational thing that we can do. And if humans try to stare at noise, we would fail just like this would fail. So I don't know how to formalize it, but obviously it's a solvable problem because nature solved it. So yeah, that's the level where we're at now. Right, okay. Yes, but now I want to address this example because this is sort of where it gets strange. So back to Zara's question about polynomial regression. So if we do polynomial regression in this example, one danger we have to be aware of is overfitting. So if we choose our, let's say our order of the polynomial in this case would be p. If this is bigger than the number of samples, then we will have one or many ways of exactly fitting the observed data. But of course, now when we try to predict a new point, we will have a large error, right? That's overfitting. In machine learning language, we would say that this model does not generalize to unseen data. So a rule of thumb used to be in machine learning that you want your number of parameters much smaller than the number of samples, otherwise you will overfit, right? But here you see this is not the case at all. Here the number of parameters is much bigger than the number of samples. And this is now a very typical situation in deep learning. It's the most typical situation. And yet these networks don't overfit so much, right? They generalize well, and they do like very, very well. And so this is the question of why this happens. It's called the generalization puzzle. And that's sort of the like underlying motivation for what I'll describe if I have time.
I understand precisely
Yeah.
the x's, the analog of what is the x, because for each pixel you have to specify the color, so like how many x's have you got?
Yes. If you want like a real...
So you have a 32 by 32 matrix of real numbers?
If you have, yes, if you also want colors, then just multiply by 3.
Okay.
And this will be D.
Okay.
Yes. If you want, you can also do black and white. Like you can do many things. But this is an example that's actually realistic.
Input is a pixel, or input is a dog and a boat?
The input of the matrix.
The matrix of pixels.
So X is like pixels, and Y is like dog.
Yeah.
Okay? Okay. Okay. So why does it work? And now I will try to sort of tie this into some of the questions that I couldn't really answer before. Well, we don't know why it works, but what we do know is that the fact that it works has to do with all three components as we described them. They all contribute to the fact that it generalizes well. So first of all, as we already discussed, the data has to be sensible. And we can make this, at least empirically, we can see this very precisely. You can do the following experiment. Take those images and take the same network as you would before and just choose random labels, right? So just nonsensical, like you have a picture of a dog, you tell it it's a boat, and just have it learn that. Because there are so many parameters, it will be able to learn it will be able to sort of memorize all of these training samples with the random labels. So if you now ask it to say what's in this picture that you already saw before, it will give you back whatever label you handed it over. So that works. But it will not generalize, of course. Now if you give it unseen pictures, it will give you a wrong label. Right? So data is obviously important. What is it about the data that like how can we formalize what it is about the data that makes it work? I think that's like the hardest question here, because the data is messy, it comes from the real world, it's hard to reason about, and I don't have an answer for this. The class of models that we choose is also known to be very important, and it has to sort of fit well with in some sense it has to capture correct priors about the data. In particular for image classification, if you try to do this classification with networks that look like this, you will not get good generalization. You will get like maybe like 50, like you will be able to, again, train on all your training samples well, but once it sees an unseen sample, it will have like an error. It will make an error 50% of the time. That's like the best you can do. So the way people get around this is by choosing architectures of networks that capture something about the input data. In terms of images, you sort of cut out some of the weights, and you sort of duplicate some of the weights in a way that captures some notion of locality of features inside the picture and captures some notion of translation invariance in the picture. So it's like it doesn't matter where in a picture a wheel would show up, it would sort of classify that as a wheel in some sense. This seems to be what's happening. And so on these networks, it's important for, like the way I describe these fully connected networks, I can reorder all the pixels, and it just works the same way. They train the same way. But on these networks that are fit for image classification, the actual arrangement of the pixels in the matrix is important.
Pixels which are very far away.
Essentially, yes, that's right. You only have like local filters Yeah. And also you apply the same filters everywhere. So, yeah. So these are called convolutional neural networks, just the thing I described. There are other examples of using these kinds of symmetry ideas to improve machine learning tasks. But that is the second part that's also very important. The third part is that the way you do the optimization is also important for generalization, because already from what I told you, you can convince yourselves that this class of models that we use, either convolutional or not, will have solutions or minima that do not generalize well. And that's pretty easy to see. But somehow, the fact that we do it with gradient descent, somehow gradient descent finds the good minima of the loss function, right? So it's also something about gradient descent that helps.
Depends on where you start. It's like in Newton's method, you may start in the wrong place and it will take you to the wrong place.
It also depends on where you start. But the modern choices for the initial conditions, what they mostly ensure, like the way it worked before we sort of found these more modern initialization methods, is that the network just wouldn't train. It would get stuck on some plateau or something. Once people figured out how to get like sensible initial conditions, it trains, but then it sort of always finds like a good generalizing minimum. Yeah.
So when these things play chess, they also spit out probabilities for which are the best moves, and then just take the best move or something.
Yeah, always, yeah. Yes.
Related to that, which is the machine, which they call Deep Blue or something, the way it played, that it would search a position.
Yeah.
In the history of all games that there was input in the machine, right? The machine had all the games that were played, basically. Then he would find the position, and then he would see how many moves have been made already for that position, and which one led to win and loss and so on, and optimize and choose the moves that most likely to improve the position.
Mm-hmm.
So is this the message that
It's a very
No.
efficient way of doing it.
No.
This is completely
Yeah.
different.
this
The-
is improvement.
Yeah, it is
The modern,
I think it worked. It had a data.
the very early ones worked like this, but the modern ones rely on no human games. They just play one against the other, and there's no human input. And they're better than like after.
They're using these things from here.
Yes. Yes. That's a field called reinforcement learning, which is a bit different because in reinforcement learning, you observe you observe the state, which is like the image. You take some action, but then the action back reacts on the state, right? Whatever.
Why don't they do that with
That one
images?
was doing that also. I mean,
What's the next step with image? Like once I classify the image, I'm like done.
You have problem, and then sometimes you know the result was good or not, and then you run it.
Well, maybe if you classify an image incorrectly, similar images would also be classified incorrectly, and you'll run into some kind of problem.
Sorry, that like if I classify image incorrectly, I back react on that by following gradient descent. But that's not part of like the dynamics of the problem. The dynamics of the problem are just given an image, predict the output. And in things like chess, it's not that you just predict one output. Then there is like some Markov process where you go to the next state, and then you need to predict another action.
Yeah,
So it's just a different setup.
That one was a combination because if you play chess like that, I mean, it plays itself, right?
Yes,
Very
plays
quickly
itself.
it cannot play anymore because there are too many ways to go. So it was a combination of the already played games.
Yes, in the old versions. Yes, yeah. Today, yes.
They completely leave the information of played games,
Yes.
and they just go straight.
There's no human input now for the Alpha 0 engine. There's yes. Well, yeah, we've come. Yeah. All right. So yes. So where were we? Generalization puzzle. We said that all the factors are important, and now I want to give more. I have like 30 minutes. Okay. So. Right, I want to give some more details on gradient descent because that's going to be the focus of the rest of the talk. So I said that gradient descent somehow manages to find minima of the loss function or low energy points in the loss function, which generalize well. Actually, I want to make a more detailed statement. So for that, I first need to explain the following. You see here we're taking lots of small steps, and at each small step we have to compute the gradient, which is a sum over all the samples. And this is, so it's like, it happens at like order n times p time. So I go through all the samples, and it takes me an order p calculation to compute the gradient. This is very, this gets very expensive, especially once we have many samples. And so what people do is they do a stochastic version of gradient descent, which, and the idea here is very simple. We, instead of computing the full gradient, we compute an estimator of this gradient. And the way we do this is, at each step, we choose a subset of samples randomly. It's called a mini batch B, with a fixed size. At each step, we choose the same size of mini batch. And then we write down an estimator for the loss function, which is the same as we had before, except we're only taking the mean over the samples in the batch that we chose. And then we're summing over the single sample loss L. So this will be, like in our example before, this would just be the squared error. So the same as before. We just do it on some samples. And with each step, we choose a different size B subset. And then the gradient descent step in this case will just be the gradient of the batch at time t. It keeps changing. Right? So it seems like we traded off. We have a trade-off here. It's much faster because B, like if n is like 10,000 or 100,000, B can be like 32. So very small. And so we do that. This is much cheaper. And the trade-off seems to be that we don't have as much accuracy, right? We've introduced some noise. Like this is an unbiased estimator of the gradient, but we've introduced some noise.
What's the intuition for picking B?
Random. You choose it randomly.
The size of B.
The size of B or B?
Well, either way. I mean,
Oh,
you take
no,
darts
these are-
and throw them in a board.
Yeah. You choose. Yeah. At each step, you choose a random sample because you want an unbiased estimator of the gradient. So you sort of have to, or that's the most natural thing. Yeah.
Are the batches fixed, or do you shuffle after each turn?
You shuffle after. Let's say that, like, ideally, what we do is actually at each step just choose a completely different batch. Not exactly how we do it, but we do something very, very, very close to that. Each step is like literally a completely new batch. Yeah. So they're uncorrelated across time. Yes. All right. So it looks like we had some trade-off here, but it turns out that actually doing stochastic gradient descent in general works better than doing full gradient descent. Works better in the sense that the result it finds, the minimum it finds, generalizes better. And this is true in many cases. Image classification, other tasks. There is something about the noise that the stochastic gradient descent is adding into the mix that's actually making your trained model better.
How deep is the descent? How many steps?
How many steps? Let's say somewhere between thousands and tens of thousands in the sort of examples we have here.
To number n or much?
Oh no, that's maybe accident. I mean, not really. No, you can have simpler examples where it's. No, I can't say that. Yeah. It really depends also on how complicated the data is. Like complicated data would need more steps to converge. Also, there's something a little bit arbitrary about this, or a lot arbitrary, because if you look at the loss over time, it maybe looks something like this. And so you sort of have to decide where to stop it. There's no like clear criterion.
Yeah. In each step, is there something which estimates that this is now a good answer? I mean, that we are basically close to truth?
Yeah, you can compute the accuracy of your predictions, and
on each.
there's a grading, and that's sort of how you decide to stop. Yeah, but it's still arbitrary because if you keep going, it gets better and better. Yeah.
So in the chess example, it just says that this position is much better out of it. Just rates positions.
All right.
Get is a higher rated position.
Chess is different in another way, which is that chess is right. Everything I discussed so far falls under the category of supervised machine learning. It's supervised in the sense that I'm providing the labels. In chess, there are no labels, right? It has to sort of, all I'm telling it is just this is a won game and this is a lost game. That's like the only label I have. And it sort of has to figure out the value of the position. And so it's not exactly unsupervised, but it's not like this.
Y in the chess case would have been the rating of the position, that this position has this kind of.
Well, how do you know what the rating is? That's called the value of the position.
Okay.
Yeah, but we don't know. We don't go and tell it this is the value of the position, right? It has to figure that out by itself. So that's why it's not exactly like this. Yeah.
There is no Y
there. Right. Okay. Yeah. So there's something interesting about stochastic gradient descent, and somehow, coming at it from a physics perspective, this looks like a very natural thing to study because there are some obvious dynamics that are going on here. It's stochastic, and it seems like a natural thing to look at. And so I'd like to, I'd like to explain is I'd like to give a story of sort of how one might try to tackle this problem, in the sense that we're going to write down a theory of stochastic gradient descent. We're going to try to make assumptions which are consistent with actual empirical observations in this problem, trying to remove our biases from physics. And then the theory, we're going to stare at it, and it's going to suggest some obvious measurements to perform. And then we can go and perform these numerical measurements or experiments and find something interesting. So we'll see how far we get with this. But the theory that you can use to model this is Langevin Dynamics. That's like a very obvious thing that people have done before. Yeah, I'll try to give. Yeah, all right. So I'll give a very brief review of Langevin Dynamics in physics, and then we'll just apply that to stochastic gradient descent, and we'll see that there are some subtle but important differences that you have to be aware of. All right. So Langevin dynamics in physics, you can, like the simplest example, you can imagine a particle in a fluid, and this particle is like swimming in the fluid, and it's colliding with tiny particles in the environment, and we want to model the motion of this particle. And so we write down an equation of motion. So we have a friction term coming from the environment. We also have a force coming from the environment. And the special thing is that we split the force into a mean. So the mean is taken over different realizations of the environment. And then we have some fluctuations in the force, which are stochastic. So it's a stochastic force. Then to connect this to, or to do the simple thing which is connected to SGD, stochastic gradient descent, we're going to take the highly damped limit. So we take the friction coefficient to be large, and we're going to scale everything such that this acceleration term becomes negligible. We don't really care about it. So we drop this. And then once we do this, we're just left with this equation, and we can rescale the friction coefficient into the time. So we can just set now gamma to 1. So gamma is very big, and then we set it to 1. Okay, so we end up with this equation, which you can already kind of recognize as the same, is like the continuous time version of what we had in stochastic gradient descent. That's good. Then the next step is to say something about the correlations of these fluctuations. So by definition, they have 0 mean. And we have to say something about their 2-point function. And the common choice, or the correct choice for this physics example is this. So there's a diffusion coefficient that comes here, and then there's a delta function. And the delta function says that at separate times, the noise is decorrelated, which is fine, and at equal times, it diverges. And the way to see that the divergence is sensible, probably the simplest way is to compute the displacement of the particle after time t, and we find that it follows this diffusion law. So this is a good choice. Then the next step we can take is to move away from the stochastic equation, which is kind of hard to reason about, and to write a deterministic equation called the Fokker-Planck equation for the distribution, the probability distribution over position space as it evolves in time. And this will be deterministic, and we'll be able to gain more intuition from it. So this has the form of a continuity equation. and the current looks like this. So now I've introduced more dimensions, and the current looks like this. So now I've introduced more dimensions. So now my diffusion coefficients are matrix. And I have this probability current, which tells me where to go. There's a drift term. And now I will make an assumption that the diffusion coefficient is constant, and the noise is constant and isotropic. And then I could pull this out, and I have like a nice diffusion term. So that's the story in physics. Right. So questions about this? I'm guessing not. Yeah. OK. So now let's apply this to stochastic gradient descent and see what happens. Right. So again, the update equation in stochastic gradient descent, I can write it like this. I will have the mean taken. So this mean is taken over all the choices of mini batches that I can make. And then there will be the fluctuation around the mean, which is due to our particular choice of mini batch at each step. And this will be stochastic because at each step we choose a different batch of samples. So you see, this is like if I do it like this, and I take a small learning rate limit, that's like going to the continuous time limit, and it's literally the same as this Langevin Dynamics equation. But now we have to look at the correlations. So we have to figure out, so again, by definition, the mean is 0. Well, what is the 2-point function? So the 2-point function of this is the same as the connected 2-point function of the loss. So it's the covariance of the gradient. And again, all these derivatives are taken with respect to the parameters. And each one of these is an average over a mini batch. And so we can use central limit theorem to estimate how this scales with the size of the mini batch. And it scales like this. So 1 over the size of the mini batch, and then the connected 2-point function for a single sample. That's just central limit theorem. And then because we are choosing a new mini batch at each step, there will be a delta function, Kronecker delta function, telling us that these are uncorrelated variables. Right? But now we have to go back and see how this compares with the physics case. And to see that, so this is all in discrete time. So this is SGD. And let's take the physics 2-point function and write it down in discrete time. What happens with physics if you do that is that it looks something like this. I discretize time in small steps. The small steps are analogous to the learning rate in SGD. And we get this. Right? And now we see that's not the same. Because here, if we go to the continuous time limit, then we have this divergence, which is necessary to get the Dirac delta function. But here, there's nothing that we can take to generate a Dirac delta function in the continuum limit. This is because the size of the batch is limited below by 1. We can't take less than 1 sample to estimate the gradient. Right?
But in this case, step is 1. Right?
Well, we can. Yeah, we can call this eta. Of course, it doesn't matter. It just no. It's no. This is just how we count steps. No, it doesn't. It doesn't change anything. I mean, in the discrete, because we start with the discrete case, the way we measure time is fake. So it's right. So this is a difference, and so you cannot just then say, well, we're taking continuum time limit. We have the physics case, write down Fokker-Planck equation, and keep going, like you will find in the literature. It's just not correct to do that. You have to go back and now derive a new Fokker-Planck equation for stochastic gradient descent. No, not because of no. We can do the physics example in discrete time, but then it will have this 1 over delta t.
So Coque-Planck is ruled out, basically.
Yes. Ruled out. Yeah, it's ruled out. Yeah.
So the vision is not randomized in time? They're not randomized, so they correlate over longer.
No, they don't. You see, I still have this Kronecker delta here. They are decorrelated at different times. The thing that doesn't happen is that the fluctuations blow up at equal times. That's the difference, right?
Is this what is called left? Discrete time diffusion.
No, I don't think so. Okay, I don't know. As far as I know, it's not this.
Discrete time diffusion.
Yeah. I mean, this will give this. Yes. I mean, this will give discrete time diffusion. It's just that the diffusion in physics is enhanced by this 1 over delta t. And in stochastic gradient descent, there's no enhancement. That's why you have to start from scratch. Okay?
Maybe physics 1 would be better, or?
Yes. So now, of course, you can, like so far I've been descriptive. You can go, because you have control over everything, you can add noise like this and see what it does. You can do this.
Does it improve?
I don't think this. Let's say this has not really been studied carefully. Yeah, as far as I found, it has not been. There's one paper on adding noise, but it doesn't address this question, right? Yeah. Okay. So, but this. I mean, this is fine. We don't have to use the physics equation. We can just derive our own. We just have to be careful, and we have to stay in discrete time and see what we get. So I'm going to write down what you get. This is not hard. Where I'm going to put it?
There's no nice continuum there.
Exactly. There's no nice continuum. That's right. There's no. Yeah.
The fact that there is no delta t in the denominator basically is a statement that there is no continuous limit.
Yeah. That's right. There's no nice continuum limit, but there are other interesting things that happen which do not happen in physics. So it's not all bad. Right? So the equation we can write down is sort of a discrete time version of a Fokker-Planck it's a Fokker-Planck equation which now describes the evolution over parameter space. So we will have an initial condition which is just determined by how we choose to initialize our parameters, and then see how it evolves, and we get the discrete form of the continuity equation. Just write it like this. So we still have something that looks like a probability current, and the probability current has a leading term, which is the full gradient. Then it has a subleading term in the learning rate. So everything here is assuming the learning rate is small. dj. This, and then we have higher order corrections. Right? So there are a few differences between this is what you get, and there are a few differences with the physics compared with the physics case, which are all due to just this 2-point function being different. One difference, as Zora pointed out, is that we cannot nicely take a continuum time limit and get rid of these higher order corrections because the fluctuations are not enhanced. So if we do that, we will also lose the diffusion term. And what we'll get is this term, which is just ordinary gradient descent. So in the continuum time limit, we lose all the stochastic nature. We just get ordinary gradient descent, and we don't learn anything.
It probably depends whether you take this parameters theta, also scale to zeta. I mean, I can pick in my hands, right? I can say these W's that you called before were actually proportional to eta or actually inversely proportional because eta is actually 1 in that example.
Well,
What we call double scaling. You scale also the parameters of your.
I mean, theta are dynamical variables. I don't control what they are. I can try to do that, but in ordinary gradient descent, eta is fixed, and theta are determined dynamically by this Langevin equation. I can't. I mean, I can go in and scale them, but that's not what we do in SG. All right, so we can't take a continuous time limit. So it seems the best we can do is to say with a fixed number of steps, we can make the learning rate small, and then we will have a controlled approximation. That seems to be the best we can do. So we're just going to do that. The second difference, which is kind of funny, is that notice that the 2-point function we got in this diffusion term is not the connected 2-point function. It's the full 2-point function. That's very weird, right? But I mean, you can track this back to like being, or mostly being due to the fact that we're in discrete time. And at discrete time, we need to make finite steps. And when you make finite steps, you can imagine that there will be parts of this expression that will have to be resummed to give you the finite steps. So this is, if you really dig into the details, it's not that weird. But as I wrote it, it's very strange to have like a diffusion coefficient that's not a connected 2-point function. Right. All right, but then we have something here, and we can now stare at this equation and see what we can learn from it. So let's open these, let's act with these derivatives and see what terms we actually get. And that's where the more interesting part of it, or the positive part of it starts. Right. So first, if we take this derivative and act on this L, right, then we will have di djl djl, and we can take out the di derivative. So we're going to do that. So we have a total derivative term. Right? Then we have the other term. This is the thing I wrote here is the trace of the Hessian of the loss function. And then we have this diffusion term. A diffusion term, but with the full 2-point function. Right? So these, and then higher order corrections. Right. So this is what we get. And I want to, so this is just the ordinary drift term moving down the gradient. And I want to focus on this term, because that seems to be the most interesting term that you get. So first, notice that it's a total derivative. This means that we can actually control the coefficient of this term up to subleading corrections by adding something to the loss. Right? So what I mean by this is that we can define a new loss, which is the old loss plus some coefficient times the norm squared of the gradient. Again, all derivatives are with respect to the tunable parameters of the model. We can do this, and this will directly affect the coefficient of this term. So that's good to know, and then we can go and experiment and see whether adding this, from this perspective, it looks like a natural thing to try. Does it help performance? Does it hurt? And so on. It's like another knob that we get in addition to the learning rate. So that's one nice thing about this term. Another nice thing about this term is that it's easy to measure. So if we think about this term, we have no hope of measuring because we don't actually have access. Like when we actually do experiments, we just have one realization that's like rolling down the hill. So we can't take derivatives really. But we can measure, we can try to measure this coefficient or this correlator, and we can try to measure this correlator. And it turns out that we're lucky, and this term, which seems weird and its interpretation is not so clear, is also kind of hard to measure for completely technical reasons, uninteresting reasons. It's hard to measure in practice. This term is easy to measure, right? So we can go and measure it and see what it does. And so now let's just summarize the story so far. We want to understand stochastic gradient descent. We have a theory that captures the dynamics of stochastic gradient descent. We stare at this theory, and it's suggesting, look at this subleading term, measure it, and compare it to the leading term, the gradient. So that's an obvious experiment now to try. You can go and try it. And the results of this experiment, I will not be able to explain in detail. That would take like another hour. But I will just summarize what you find and then how these observations might be useful. All right, so you go and measure these. So let's give these some names. Yeah, yes.
Your point is that instead of doing this stochastic sampling, you can instead just change the loss function, and it's more or less the same.
That is one point, which is like some sort of renormalization effect. That is one point. But now I'm saying even simpler than that. I just, without changing anything, I just want to see what this term does in ordinary stochastic gradient descent, and this is what I measured.
Well, if you're at a good minimum, then it's zero. That's the only thing. It's a good term to add because it's zero. It's a good minimum.
Well, I mean, we already know that there are like many I mean, there are many bad minima, and it will be 0 in all of them. So I really can't predict what it's going to do. Yeah.
Is this the function of time?
Yes, I'm sorry. Everything here is a function of time. Yeah, everything. Yeah.
It will be very helpful for those who knows Langevin
Yeah.
and stochastic equation, but don't know what machine learning is.
Yes?
Show this dictionary between one terminology
Yes.
and another terminology.
Okay.
What is what?
Yes.
Suppose we know all very well Langevin Dynamics.
Yes.
But
I sort of have been assuming this. Yeah. All right. So Langevin and SGD. So or machine learning or deep learning, whatever. So in Langevin Dynamics, we will have the potential. This is the loss function. We have our position. These are the tunable parameters of the model. Theta. The tunable, the weights. The W's. Yeah. We have what else? The learning. We have if we discretize time, we have small delta t. This is the learning rate. So learning rate. Diffusion matrix is, as we saw, there's no exact analog, but it's roughly the 2-point function of the gradient. Sort of. Yeah, I think that's. Yeah. And probability distribution and current are the same.
I see. And this diffusion coefficient data are taken from the database, from analysis of the database.
This?
Yes.
In physics?
No.
Well, you know better. In SGD?
Yes.
You can go and measure it.
You measure it based on available data.
Yes. Yes.
And that's an input to the Langevin Dynamics.
Yes, that's right. Mm-hmm. Well, I should say another thing that's different than physics. In physics, we can go very far by saying that this is isotropic and constant. In machine learning, this is not at all isotropic or constant. So.
And I and J, it's a huge multiple dimensions.
Yeah, dimension I and J go up to, let's say, 100,000. Huge dimension. Huge dimension, yeah. Okay. Yes. Yeah, that's good to know. That's good to know. Okay, I should have done that before. I'll keep this up. All right. So now some results. Yes, yeah. Yeah.
So there is two parameters. One is 10 to the 5, it's the dimension of the space, and discretization, rate of time, discretization of time.
Yes.
One goes to 0, increment of time, maybe.
The number, you want a number? It could be 0.01, 0.1. These are typical numbers.
Which one goes faster? One goes to infinity, that's a limit, right? 10 to the 5, it's infinity.
This is fixed. This is it's large, but a fixed number. It doesn't change.
But
He's
if
asking
I think about the limit, that's what goes fast. This is what goes first. Limits do not commute typically, right? And
Sure.
Which one goes to infinity, to 0 first?
Well, that really depends on what you want to do.
Yeah, probably.
I don't have a natural answer to that question. People do both. People definitely take both. Yes. Yeah.
Well, we don't want to learn forever.
No, you don't. I mean, continuous time limit is infinitely many steps, but it's not learning forever because we're just now measuring time in a different way, right? Yeah. But
So we would explore
yeah.
very large, high-dimensional space, but by finite time, or we have infinite time in our disposal.
No, we have. I mean, we have computers, so we have finite time. Yeah. Yes. This is supposed to be practical in the end. So yeah. Okay.
But it's an interesting question to ask how you should scale these parameters.
Yeah, and people ask this question. Also, you can sort of see from here that there's some relation between the learning rate and the batch size, because again, the way we, like going back to here, we had an estimate of this 2-point function, and we said that it goes like 1 over the size of the batch. And so you see that there is a natural ratio to look at this seems to be a natural thing that people definitely look at and do experiments with. And
actually, that was a question. The theta times eta was something that I was saying that might lead properly adjusted to continuous limit. You see, you have theta which goes to infinity, 1 over theta which goes to 0, and eta which goes to 0. And if I relate them somehow and make their ratio finite, or maybe there is a continuous limit. I mean, it was tried.
I'm fairly sure this was not tried. Yeah.
Yeah, what you said is usually, we call it naive continuum limit.
Right.
It
It
does not exist, as you explained.
Yes.
I asked
But the question is whether there is some...
double scale.
That's a good question, and I'm pretty sure this has not been tried because this whole story, as far as I can tell, has not been appreciated in the literature. I mean, just this fact that you have to modify the equations. I mean, maybe mathematicians sort of appreciate it. It's buried in some of those papers, but the more like practitioner side of the community, which does more experiments, is not aware of this. Yeah, that's I'm fairly sure.
I see. So there is an open question how to formulate this SGD in terms of diffusion. Which
Yes.
way
Yeah.
to take, how to
Yeah.
In terms of stochastic equation.
How to take the continuum limit? I don't know how to do it. I'm pretty sure it's an open question. What you find in the literature, people talk about diffusion and so on. They just use the ordinary Fokker-Planck equation. Yes, there are many papers like this. Yeah.
So you can try to summarize.
Okay. Yes. Okay. So we talked a bit about what is deep learning, and we presented one open problem in deep learning, which is the generalization puzzle, which is the question of why these networks manage to train well and generalize well despite having many more parameters than training samples. And then we sort of went through a physics way kind of thinking exercise of trying to model the dynamics of stochastic gradient descent, which is definitely an important factor in generalization, and just writing down the theory and seeing what does it tell us to do, what sort of experiments should we do, and then we can go and measure and go back to theory and so on, and that's like a continuation of that story. But yeah, I think I'll stop here.
So just to finish your beginning to say, so how the first line compares to the second line?
Yeah. So call this let's say this is G, the gradient, and call this vector. There are two vectors, right? V. So you go and measure them, and you find that very quickly, like after about 100 steps of training, they become closely aligned. So you measure the overlap like this, and you get big numbers, like between 0.9, 0.95. So these are two different vectors in like 100,000 dimensional space, but they become closely aligned, right? Another sort of small comment is that if you open the brackets here, what you find is that this is the Hessian acting on the gradient. So it's like you can think of the gradient becoming approximately an eigenvector of the Hessian, approximately. In fact, the story is more involved, and it's not exactly an eigenvector of the Hessian. What happens is that the spectrum of the Hessian, once you diagonalize it, has two components. One component is a top component with a few large positive eigenvalues. The dimension of this of this small subspace is k. K is the number of classes in our classification problem. And then there's a huge bulk which includes many small eigenvalues, so about, let's say, 100,000 eigenvalues, which are small. And once you dig in, what you find are two things. One is that the reason this happens is that the gradient becomes concentrated in this tiny top subspace. Within this subspace, it's like a random vector. But because of the way the spectrum is organized, the random vector in this top subspace will give you large overlaps. That's one observation. The second observation is that this top subspace is approximately preserved over time. So the eigenvectors that span the subspace rotate very quickly. But you can look at the span of them at different times, and you will see that that thing decays quite slowly. So in the end, you find that the gradient tends to live in a tiny subspace, which doesn't change much over time. And then it's a very small step to show that the main effect of gradient descent. The main thing you get when you do gradient descent, the fact that the loss decreases, just comes from the gradient projected onto this subspace. So all the interesting stuff seems to happen in this tiny subspace.
You can reduce the computational complexity immensely.
If you can figure out what the subspace is, which is not so easy because you have to do like a partial diagonalization of the Hessian. It's not clear yet. And that involves still looking at like all the parameters because these are not like sparse vectors. These are, yeah. But there are definitely things to try. Yeah.
Does this understanding help you to choose batch size or to do some practical things? Suppose that you know everything about stochastic gradient process. So gradient distribution.
I don't know if this will tell us how to choose the batch size. This might lead to like improvements on SGD, like different optimization algorithms. For example, one optimization algorithm, like gradient descent, that just looks at first order information and derivatives. You can look at second order information and do something like Newton's method. And when you do Newton's method, the update, this is just one example. The update is, you need the inverse Hessian acting on the gradient. This is like the best you can do with second order information. And this is unfeasible for two reasons. One is that this Hessian is huge. You can't even write it down, like let alone invert it. And the other reason is that it's not well defined because it has tiny eigenvalues and zero eigenvalues. This suggests that maybe you can actually do this if you focus just on this subspace. And in this subspace, all the eigenvalues are positive, and you can invert, and it's much easier. So that's like one thing. There are like many things to try, which we haven't tried yet. I should say this was with Dan Roberts. I mean, not this, but all these observations are with Dan Roberts and with Ethan Dyer.
Let's just ask it in this question session. There will be a Q&A session. Yeah? So that's the thing.
Thank you.
Now you can ask.
Christian,